Hello students! In this video we are going to discuss the guided study for learning target AD6, Introduction to the Antiderivative. In this learning target we are going to find a function's general antiderivative, also known as the indefinite integral, using knowledge about derivatives and what we'll state below as the definition of antidifferentiation. So the antiderivative is, as the prefix anti might note to you, the reverse process of differentiation. So here we are reversing the derivative process. Conceptually, you could kind of think of this as an inverse, right? We're going to be given a function and we're going to be told that that function is the derivative of some function out there. What function is that? So we're almost undoing the differentiation process when we find an antiderivative. We're almost undoing the differentiation process when we find an integral. And for now, I would like for you to please ignore these things in this definition and just focus on the relationship between big F and little f. According to our definition, a function big F is an antiderivative of little f on an open interval I, provided that that big F is f of x's derivative. So big F is little f's derivative. In this case, in mathematics, the notation big and little letters do potentially indicate different functions, and oftentimes they do indicate different functions. If I write down a function named big F, it's probably different than a function named little f that I might write down later. The notation we use involves this integral symbol, and we'll re-emphasize this in class. This is the integral symbol, and every integral symbol must be accompanied by this differential. For right now, I would like for you to get comfortable seeing this notation. We are going to talk about what exactly this is in the coming up I unit. In I1, we're going to discuss Riemann sums, and we're really going to emphasize what that dx means. But for right now, for the purpose of AD6, let's focus on reversing the process of differentiation. And in this case, the answer to the integral, the antiderivative, is going to be a combination of the sum of a function, little f, and the constant of integration, which is what this is called. I'm going to explain why the constant of integration is necessary in this video. For now, though, I just want you to see anytime you write the answer to an integral, this constant of integration must be included. So for example, letting go right now of the notation. For example, if I tell you a function f prime equals 3x squared, and then I ask you what f is, actually, this statement right here and this statement there are equivalent. Okay, I could rewrite this statement as the integral of f prime of x equals 3x squared. No, the integral of f prime of x equals the integral of 3x squared. I need my differentials though. And it's going to equal the function f of x. And in a moment we're going to add that constant of integration. I'll explain what that means here. But again, I don't want you focusing on this notation just yet. I want you focusing on what this question specifically is asking. If I hand you a function and I say, here is a derivative. Here is the function 3x squared. Please tell me what function I would need to take the derivative of to obtain this answer. What is f? While many of you remember the power rule, I just wrote an integral symbol, d dx of x to the n equals nx to the n minus 1. Well, here I have a 3 as the n in the position of the answer to the derivative, and then I have 2 minus 1, or I have n minus 1 in the exponent as well. So if n equals 3, n minus 1 is 3 minus 1, which is 2, which is what we see there in orange, meaning that the function f of x must be x cubed. Right, and we know f prime of x, 4x cubed, is 3x squared, which is exactly what we have here. These two match. But I ask you this question. What if I said, but f of x could also be x cubed plus 1? Is the derivative of that function also 3x squared? Yes, because the derivative of a constant is 0. So in this case, f prime of x is also 3x squared. And I could change this number 1 to any number on the planet. 44, 92. So what we do as a placeholder for any constant on the planet is we add plus c when we state the antiderivative. So the best antiderivative of this f prime function is f of x equals x squared or x cubed plus c. Now, this happened to be really nice because we could literally see that in front, given the derivative, matched the exponent we needed. But what if we didn't have a constant in front? So if I ask you for f of x giving x prime equals x cubed, what is f of x? Well, we know from the power rule that in order to state f, this must be 1 bigger. So we can start there and we can say, okay, what if f of x is x to the 4th, right? Knowing that f prime of x for x to the 4th is 4x cubed. We're off by a constant, right? When we differentiate that, we get 4 times x cubed. So if the question asked if f prime is 4x cubed, what is f? We would say x to the 4th. So what do we do to compensate for that? Well, we want this to be divided out by a constant number 4. So we'll divide out our original guess by a constant number 4 and guess again. I don't want you guessing. Later you're going to be given formulas and you're going to get kind of quicker with this, but for sake of illustration of what the antiderivative actually is, which is super helpful versus just throwing formulas in your face and saying, here, memorize them. Nope. Now we'll guess again as x to the 4th over 4, but we also have to remember I could add 1 to that, I could add 44 to that, I could add 92 to that, I could add any constant number to that. So when I state what f is, and forgive me, I put a prime there, that should just say f. When we state what f is, we always remember to add the constant of integration. And we can check by differentiating dx of x to the 4th over 4 plus c is 4x to the 3rd over 4 plus c, not plus c because the derivative of the constant is 0, so that now matches. 4x cubed divided by 4 is x cubed, and that's exactly what we started with. And then I encourage you for our last example, which we'll talk about more in class, not to forget all of your other derivative rules. The derivative of the natural log function is 1 over x. The derivative of e to the x is e to the x. The derivative of sine x is cosine x. So I could hand you the cosine function, say that it's the derivative of some function, please tell me which one, and your answer would be sine x plus c. Here I'm handing you the function 1 over x. I'm saying here's a function, it's the derivative of some function. What function is it the derivative of? It's the derivative of the natural log function. But remember also, I can always add a number to that, and it still differentiates the same. So in your guided study, I'm going to put a few more examples very similar to this that use the same concept, and I want you to do your best to try to determine what the antiderivatives are.